I must admit that I started panicking when I was contacted by the organizers to give a talk. It's happened a few months ago, because I haven't done anything substantial on the conference topic. So I quickly teamed up with a graduate student from Croatia. His name is Tonći Crmarić, and we tried to prove something that would be somehow, at least that would be deservedly presented here.
You follow the steps of freedom as Arab.
Yeah, okay, it's good to follow great people. Well, luckily it worked out. I mean, if it didn't work out, you wouldn't know it, I wouldn't tell you. I would be presenting something else and still trying to sell you the same story, of course. That's how it is. And also, the topic is simple enough that I will even be able to cover most of the technical details. But all details can be found in the preprint, which is on the archive, but it is not updated because now we have the third author who greatly simplified one of the proofs to the extent that I don't really like, because before I had some really ugly and nasty computations, and I was trying to catch up with yours to show you that I also have some computer-assisted parts of the proof. Now this is all gone, and I'm afraid that all arguments that you'll see are somewhat elegant. I'm really sorry about it. Okay, and what is the topic? The topic is actually motivated by notions from additive combinatorics. So whenever we have a subset of the d-dimensional integer lattice, you can define something that people started calling the additive energy of the set. And this additive energy is pretty much just the number of solutions that this equation has in the set A, right? So the number of 4 tuples in the set A that satisfy this linear equation. It's very simple enough to be omnipresent everywhere in combinatorics. So it has not been introduced by Tao and Wu. It naturally appeared many times, but maybe they gave it a name. I'm not even sure about that. But it's actually a very standard thing. And actually, many famous results in additive combinatorics can be roughly stated or reformulated as saying that we want to somehow characterize the sets that are nearly extremizers of the inequalities for the additive energy that have a nearly maximum possible additive energy. And what is the theoretical maximum here? Well, without any constraints, this additive energy is certainly less than equal to size of A cubed. Of course, if you take 3 points from the set A, well, you might wonder if the 4th point is also in the set or is it not, but that's the theoretical maximum that you can have. Okay. However, this notion of additive energy has been generalized by many authors. So I think most notably it has been generalized by Shannon and Skredov. In particular, it is Ilya Skredov who wrote something quite substantial, like a treatise on several possible generalizations of higher energies, and he proved the relations between them, and it's actually a bit longish paper that contains like pretty much most basic relations that you can think of. It is this second paper of Skredov. And more related and more relevant to the present setting, there is a recent paper by Chalmers de Diospont, Rachel Greenfeld, Pata Ivanishvili, and Jose Madrid, who actually preferred these names for some of the generalizations. But all 3 generalizations that you see on the slide have already appeared in Skredov's paper. And he discussed these generalizations, even though he might not give them the same names, he might not have the same notation, and so on. But the 4 authors actually called the first generalization the higher energy. So now you can think of solving this system of linear equations, which is simple enough, right? The pairwise differences between pairs of points in A should all be the same. You'll see how this naturally maybe appears analytically. And they also call the K additive energies pretty much all solutions in A of this single linear equation. But on the left-hand side, you have a k-fold sum, which will somehow be relevant compared to k-fold convolutions and such. But there is a third notion that was also studied by Shkredov, and which was not studied in the context that I'm interested in. And I don't even know how to call them, so I simply denoted them P sub k, because these quantities are counting k parallelopes in the set. So what is a k parallelope? Which it is a 2 to the k tuple of points of this form. You have like a base vertex, and you have k vectors, right? And you move from A by some subsum composed of these vectors, and all these points should be in your set A, right? Okay. So it's just a moment's thought to realize that all three generalized energies specialize to the usual additive energy when k equals 2. Right? It's just a matter of how you write this equation. Either write it with a difference, or with a sum, or with a parallelogram, right? Which is actually what those 4 points are. All right. Okay, so this is actually the quantity that we're interested in. It's actually analytically even somewhat the most pleasing, you'll see in a moment. So let's suppose that we actually want to study this certain type of additive energy later. Okay, now going back to the basic additive energy, a reasonable question is if you can say something more, or if you can give some better bound for the additive energy, if you have more information about this, about your set. So if your set is the subset of the binary cube, can you maybe have a sharper bound that is available? I'm not even calling this the Boolean cube or the Hamming cube, because this is really just a binary cube sitting inside the integer lattice. So in all those quantities, in all the sums, you are allowed to go outside of the cube, right? The operation happens in ZD. It's just that a set is contained in the additive cube, right?
You consider mod 2 or what?
No, not really. I consider it as a subset of ZD, so it's a characteristic 0, right? It's not a Boolean type of result. It happens that my set is a subset of 0, 1 to the D. I just want to say, with this extra information, can I say something more?
Did people consider mod 2 or something?
Mod 2 is very different, because additive structure is very different. Yeah, it could be considered, but for that particular type of problems, I just followed the existing line of research here. Of course, it makes sense to consider mods 2. Some of these questions might turn out to be too easy though, but yeah, we can always fix that somehow by cooking something else. Okay, so several years ago, Kane and Tao showed the sharp estimate for the additive energy of such sets, and it turns out, maybe a bit surprisingly, that a sharp exponent is log base 2 of 6, right? And actually, it turns out all estimates on this particular slide are sharp simply by taking A to be the whole cube in any number of dimensions, right? All estimates we're interested in are somehow dimensionless, and those particular are maximized for the whole cube, which will not always be the case, of course, but in this particular case, it is the case. Then for the more generalized energies, Chalmers, Rachel, Pata, and Jose showed that the sharp exponent is a binary logarithm of 2 to the k plus 2 for every k greater than or equal to 2. And in the case of those k additive energies, the sharp exponent is a binary logarithm of 2k choose k. You always guess what the best exponent is by plugging in this set, and then you try to prove it. So here I only help to complete the proof for k is greater than 100, because all that was left from their paper was just a single 2-point inequality, as Joris would call it, which was open because it was somewhat ugly. It was a finite sum of binomial coefficients squared and so on. But pretty much, I don't deserve any credit here. I just kind of played with some elementary inequality to finalize their proof for every k. I had some fun with computer-assisted verifications here, at least. So, okay, I'm fine. Okay. Now, the next natural question is, of course, what can be said if A is merely a subset of the discrete cube, and not really a binary cube, but maybe a larger ternary cube or something larger than that? Can this additional information also be used to say something meaningful? Well, here's a problem. If you want to prove the sharp estimate, then you're going to see later how it somehow transfers to a certain maximization problem. And when I had some fun running this optimization problem numerically, I found out the sharp exponent for the case of the ternary cube and for the usual additive energy to be this ugly number. And I didn't have a certificate, but I believe Mathematica gave me about 10 digits quite reliably. And when then you use some tools like the inverse symbolic calculator and stuff like that to try to figure out, is this some meaningful expression? It turns out that it probably isn't. It's just some quite arbitrary number. So we're stuck. There's no really hope, yes?
What subset leads to that exponent?
Oh, that's a very good question. It's not even clear. There is no single subset, there is a sequence of subsets. So it's actually very, very interesting, and of course the four authors from before deserve credit for that. This will be equivalent to a certain optimization problem, but not for sets, but for functions. There is a maximizer, which turns to be corresponding to a sequence of sets extremizing this inequality. So there is no single set extremizing it. On the other hand, even for the function, you still don't know what it is, because it's just some 3-valued function which is ugly, and I have no idea. Yeah. I can only give, again, a numerical estimate of the extremizer in the set of functions. But you'll see it later. In short, it's not that simple. No, I don't know. But the thing is actually that now we give up the hope of having exactly sharp exponents. So the next best thing is maybe to study asymptotics, right? Maybe to study asymptotics as either n, the size of the cube, goes to infinity, or maybe this parameter k goes to infinity, right? What is the parameter k here? We don't have it yet. Here, the author so far considered only additive energies in the usual sense. So it turns out that Shao this year, in a recent preprint, studied precisely the optimal exponent Tn in this energy estimate for the discrete cube of side length n. And he proved a quite non-trivial result. He proved non-trivial asymptotics from below and from above. So in both cases, both the lower and the upper bound are of the form 3 minus a constant over the logarithm, which is unsurprising because you would expect as n grows, then you lose any information and you approach to the exponent 3, which is the largest theoretical possible. But the question is how fast you approach this number, right? So from above he gets some really implicit constant c coming from many arguments in additive combinatorics. I'm going to say a few words about it later. But from below he has something very concrete, which he believes is optimal, but it's not known yet. But in any case, I'm just trying to say that from below you have a sharper estimate or a better guess what it is exactly, maybe. Supposedly this is equal, but you don't know. Okay, so what are our results? So we want to study those generalized energies P sub k. I will also motivate them from the other viewpoint, from the analytical viewpoint, but let's suppose that you want to study this P sub k, which is, I remind you, you're just counting all k parallelopes inside the set. They can be degenerate, right? Doesn't matter. Even though if you're in very high dimensions, and if your set is very large, not that many degeneracies will appear. So, but it's okay. It's easier to count together with degenerate cases. And let T sub kn be the optimal exponent in this inequality. We wonder about particular values, the asymptotics, and everything. And we could prove the following three results. First, for the binary cube, you can again compute the sharp exponent, and it turns out to be binary logarithm of 2k plus 2. That's an exact number. That this is sharp. Now, if you fix k, consider just 2 parallelopes or 3 parallelopes and so on, and let n go to infinity, we match the bound that Shao had, right? From above, you can have the same type of estimate, we don't know better, but from below, we have just some different constant depending on k. But again, it's of the similar form, it's k plus 1 minus a constant over the logarithm, same here. So this is the best we could do. However, if one fixes the cube, right, and lets k go to infinity, then we can do much better, and we have a very precise asymptotics. It's just this number, which you see that grows like log k, right, times some coefficient, and the next term is also known, right, the free term, and then you have an error, an additive error that goes to 0. So we do not only clarify the asymptotics, but it's even better, up to an additive error we know what it is, right? We know the difference of these two quantities goes to 0. And what is the denominator appearing here? H sub n minus 1. Well, H sub m will denote the entropy of the symmetric binomial distribution composed of m independent trials. Right, so you can write it down explicitly. This is the binomial distribution, of course. So this is just a number, but this is like the meaning behind it, of course. Even though you might not even think in terms of probability, you can just think of this as a number that appears somehow magically in the proof. You'll see where. Okay, so here are the three results. I still did not explain how this entropy comes into play. I'll leave this as a cliffhanger and switch to the other part of the motivation, which is a motivation from analysis. So many times in analysis you can prove sharp inequalities, right? Sharp inequalities is either on the discrete group or on RD and so on. These have been studied a lot. So on the discrete group, which is our setting, you have many such inequalities. They're not even very difficult because here the extremities are kind of simple. So by these inequalities, I mean Hausdorff, Young's convolution inequality, and all those things. These are very simple inequalities. You can ask also what changes if the support of the function is contained inside this discrete cube. Can you do any better? Right? Can you beat the sharp inequality we had before? So can these inequalities be refined? Here's just a very quick example to somehow assure you that it's not entirely trivial. So only this year, Shao published a proof in the very same paper of the auxiliary estimate that he needed. So he sharpened the Hausdorff-Young inequality on Z for a particular case of exponents, 4/3 into L4. This is a very, very well-known basic inequality for the Fourier transform. You can arrive at this inequality by interpolating from 2 to 1 infinity, the sharp constant. Again 1, because this is extremized for functions that have a singleton as a supported on a single number. Right? It turns out that actually you can sharpen this by knowing that your function is supported in an interval of integers of length n. Actually, all you need is that the support itself has cardinality at most n. Actually, that's all that is needed for this particular case. And Shao could prove the following. He could have changed the exponent on the right hand side. So it's not really a matter of improving the constant. Of course you cannot do that because you know for the singleton itself the constant is 1. You cannot do any better. But you can improve the exponent because of course the right hand side only gets smaller as the exponent increases. So if you can prove this with a slightly larger exponent, you have a refinement of your inequality. And he could do the following. He could find an absolute constant c, so that this inequality holds for something slightly larger than 4/3, and here is how larger. So you only need to subtract c over log n from the denominator, right? And that's actually the correct growth. You don't know the constant c. The proof gives some ugly number, quite implicit one, but this is actually the optimal growth in terms of n.
Stupid question. If instead of z you consider r and you cut from...
That's a very meaningful question. I would expect something similar, but it hasn't been written down. It might have a similar proof. We can look it up, but it's a very meaningful question. Yes, it is. Kind of. Yeah, sure.
But all this like Beckner proof, there's fantastic proofs.
Yes, even though this kind of uses the known literature, so I can tell you what the other result would use. So Shao admits that this both is and isn't a new result, kind of, because what he uses and what many such inequalities that you would write would use is a characterization of near extremizers of the corresponding inequality. Right? So if you are actually far from the extremizer, that's okay because you have an improvement in the constant. On the other hand, you have a certain loss in n by increasing the exponent, but you have a very precise information about the support, so this loss is controlled in terms of n. So those two cancel each other and you still win. However, if you're close to the extremizer, then you do it somehow manually. It has to be done like directly, estimate, whatever. But here, this is not very difficult because you're close to a singleton, right? It shouldn't be too difficult. And that's how he does it. But he couldn't really use the result by Carl Lambides and Mike Christ, or the Eisner-Tau characterization of extremizers. The latter paper is like very general in all compatibility groups, because he wanted to be explicit, kind of. So I think from the latter paper dimension, you cannot really see how these constants behave, like asymptotically. From the first one you kind of can, but he still wasn't sure. I think he really wanted to be explicit. So he pretty much redid those proofs from scratch, and that's the hard part. That's where he needed many ingredients for additive combinatorics, like some inverse theorems and such. So it's actually a non-trivial result. So on the real line, you would probably use Mike Chris' paper that actually is sharpening the Hausdorff-Young on the real line and stuff like that. Yes, I guess this could be doable if anybody wants to do that. Okay, and we can also introduce very natural norms. These are called the Gowers uniformity norms that appear in many places in combinatorics. They were devised by Timothy Gowers to somehow try to capture the arithmetic progressions inside sets. They turn out to capture a bit more, some nil sequences and such, but they're actually interesting quantities by themselves. You see, you have a multiple product of a function where you plug in all to the k vertices of this supposed parallel, k parallelotope, and sum over all k parallelotopes, and then take the 2 to the k roots to have the right homogeneity. Right, this is a complex conjugation, but we don't really care if we plug in positive functions. We can note that our generalized additive energy is simply obtained by computing the Gowers norm of the indicator function of the set itself and raised to the k. It's nothing else than that. So again, here people started sharp estimates for the Gowers norms. All right, it turns out that there is a sharp exponent p sub k, and it turns out to be 2 to the k over k plus 1, so that this inequality holds. Of course, it holds for any smaller exponent too, but this is actually the largest one that you have. So Polona and I have used this inequality many times, and many people use it. Even though it's a very simple inequality, it's still very useful, right? Whenever you need to bound, you can bound in terms of a certain size of a function. It's a certain single scale inequality, admittedly, it's not very, very deep, but it's actually very useful. Now, our main question is, okay, what is the optimal exponent in this kind of inequality, knowing that your function is supported in this discrete cube? We will see, quite surprisingly, that the two problems are related, and the sharp or optimal exponents are related by the following relation. Their product equals to the k, which actually makes you transfer from one problem to the other, whichever you find easier, right? And here is a very precise formulation of those equivalences that we had to prove in the paper, even though morally it is Chalmers, Rachel, Pata, and Jose who should be credited, because we're morally just imitating their proof with necessary changes, but it's more with the same scheme of the proof. They did the same for these energies, the k-additive energies, and for the k-fold convolutions on the left-hand side instead of the Gowers norms, right? That's the only difference. Of course, something has to be different in the proof, you'll see, but I'm just saying, morally, the ideas came from their paper. So how do you prove those equivalences? And what are those equivalences? First, the following are equivalent, right? Whenever you have two positive numbers, p and t, that multiply to the k, it's equivalent to have this one-dimensional inequality for every non-negative function on the integer supported on 0 to the n minus 1. This part 1 is probably the simplest, because this is the optimization problem in n variables. That's it, right? Okay, for each p, which is not given beforehand, that's the tricky thing. So for each fixed p, this is an optimization problem, and you hope that actually the inequality holds for each fixed p. But you want to find the largest p for which this inequality holds. However, it's still conceptually simpler than the d-dimensional problem, because it's equivalent to a dimensionless estimate, which holds in any number of dimensions. So for all functions in z to the d supported in the discrete cube, and this is equivalent to having an upper bound for this generalized additive energy p sub k in any number of dimensions and for all subsets of the cube. So for fixed dimension, you do not have equivalence. You only have equivalence if you ask for a dimensionless bound, right? And everything is also equivalent to just having an upper bound with some constant. So pretty much the equivalence of 3 and 4 tells you if there is a constant that you see on the right hand side, it will disappear. Necessarily, it will turn out to be 1.
So what is the connection between constant p in 2 and constant t in 3? It's exactly pt equals 2 to the k?
There is only constant here. Where else do you see a constant?
Yeah, pt is.
There is p in 2 and t in 3. Yeah.
Oh, you mean p?
Exponent. Yeah.
Oh, the exponent. Okay. You mean this p and this t? Oh, yeah. This is the relation. Yes. So this is the key. So anytime you have equivalence, I mean, whenever you have this property, you have the equivalence. So obviously, the largest p and the smallest t are also related that way. And from this, you also see that there is a largest p, because this is simply just an optimization problem in finitely many variables. So by compactness arguments, it actually exists.
Can I ask an idiotic question? Is equivalence of 2 and 3 like T1 theorem for this oscillatory integral?
Essentially, right, one direction is trivial, the other direction is certain layer cake decomposition, and this will be done very quickly. This is what those 4 authors actually did, so pretty much that part is just literally copied. It's just a layer cake decomposition, but let's see very quickly what the proof actually has to offer. So the most substantial implication is 1 implies 2, so actually see that this one-dimensional estimate implies the d-dimensional estimate. That's pretty much the only thing that is kind of not automatic, that is kind of difficult. But actually in this abstract setting, it's still easy. So the assumption is that you have a one-dimensional estimate, which you can rewrite this way, right? When you write what the LP norm is, and when you raise everything to the 2k power, this is what you get in 1D for arbitrary function g. So we proved the d-dimensional claim by the induction on d. The basis could be d equals 0 or d equals 1, which is just this case. So what do you do in the induction step? You start with your function and consider the slices or the sections, right? By freezing the last variable. In this way, you obtain d minus 1 dimensional functions to which the induction hypothesis applies. And now start with your d-dimensional function f and expand this Gowers norm raised to the k as a certain Gowers inner product, which is pretty much the same integral that you had before, but now when I'm freezing the last variable, the functions are actually different. I'm not seeing the same function, I'm seeing different functions because I'm freezing the last variable. So it's the same kind of sum, right? But I'm seeing different functions, so this is usually called the Gowers inner product instead of the Gowers norm. But actually there is something called the Gowers-Cauchy-Schwarz inequality, which immediately bounds this by the product of the norms of individual functions, and by the induction hypothesis I can bound each of these by the LP norm. So it actually, from this point, it actually remains to imply the one-dimensional inequality just to these numbers, right? To the one-D function consisting of the LP norms of these sections themselves, and you plug this here, and realize that the full LP norm is consisting of the LP norms of the section and LP of LP that, and you're done. It's actually quite amazing that it's so simple. It's even simpler than the proof given by the four authors because they need to consider the Fourier transform. We don't, which is kind of expected because the higher degree Gowers norms for k's at least 3 are not expressible in terms of Fourier transforms. Only the second one is. Higher are more convoluted, more complicated one. Okay, and the other thing that Sasha asked about is this direction 4 implies 1, because this is all that is left, right? This is trivial, just plug in the indicator function of the set and realize that there is this relation, right? What is p is 2 to the k over t and blah blah. And also this implication is trivial because this is a constant 1, this is just any constant. So you just want to prove that this estimate proves the 1D estimate for the functions, not for the sets. So this is just the layer cake decomposition. Once you start with 4, you can realize that this is just an estimate for the integrated functions with some constant, however you call it, c or d. Now do the layer cake decomposition over an arbitrary function, like slice it, chop it up into not too many pieces, into controllably many pieces, depending on the dimension and so on. And apply this particular estimate to each of these functions, right? These are the indicator functions, so I have the estimate. And this is just some error which is easily estimated. It's actually small in the uniform norm. So in many ways you can just bound it by the LP norm of the function itself. And add it up using the triangle inequality for the Gowers norms. And you almost get what you wanted, but you have a constant. And it's even worse, actually, it also depends on the dimension and on the cube, right? It depends on everything. But now you do the tensor power trick, of course. So since this has to hold in all dimensions, start with the function which is your favorite function tensored to the d's power, and take the d's roots, and in the limit this constant disappears and you get 1. Right? So this last part is just literally copied from what it did, and essentially it's just layer cake decomposition. Okay. We're done, and now we can finally, in the remaining time, very quickly, we can actually go over the proofs. And the proofs are now like, well, I mean, at least mostly just somewhat computational, right? So for the binary cube, you want to compute this sharp exponent. So one only needs to prove this one-dimensional equality for functions that are supported on a 2-point set. So pretty much, if you and for this conjecture, the exponent t. But just by substituting this to be x, this to be y, you have a 2-point inequality that looks like that. And it's a very simple one. So it's a straightforward generalization of something that Kane and Tao called an elementary inequality, because they consider the case k equals 2. And it's way simpler than the 2-point inequalities that you get in other problems. For the higher energies, at least you have something that involves like certain powers of differences and sums. Or for the k-additive energies, you had some ugly sum of binomial coefficients. This is actually the most faithful generalization of the Kane and Tao of 2-point inequality, and it's done very, very easily. You can give it to calculus students, but you would trick them because it's not really just differentiation. It gets ugly because the exponent is ugly. So you still maybe need to split into some cases. It's misleadingly simple, but after all, come on, I mean, aside is just sum of 3 terms, it cannot be difficult. I'm not very serious. Okay,
But
so
it hints that there is probably even better inequality, you know?
Depends how you cook it up. I don't know. Try to find one. The exponent cannot be improved, but
No, I mean that
some combination on the right hand side.
sort of Bellman function stuff or something.
Yes, because this is saturated when x and y are either the same or one of them is 0. So maybe you can convolve something to have more extremizers. That might be possible. It might be possible. I don't see immediately how to do that, but yeah, could be a nice thing to do. The next thing that we're gonna do rather quickly is asymptotic estimates as the side length of the cube goes to infinity. So we're fixing k and letting a go to infinity. So here is the lower bound that can be rephrased as this, right? You just need to prove that the limit for this is at least this quantity. This is the lower bound that we need to prove. So here is the catch, and of course it has already been used by Shao. It's also not terribly original here. The catch is actually to compare everything to the case on the real line. So on the real line, it also makes sense to find the Gowers norm. In the same way, you're just integrating instead of summing. It all makes perfect sense. And Eisner and Tao, about 10 years ago, studied extremizers of this inequality and also studied the sharp constant in this inequality. The sharp constant is not something crazily complicated. It's just an application of the iterated Sharp-Young's inequality, pretty much. But then classifying extremizers is not so easy, and this is a difficult part. But we don't even need that. We just need that this inequality is actually an equality for Gaussians. There are other extremizers. All extremizers are just characterized as polynomial modulations of Gaussians by polynomials, complex polynomials of trigonometric polynomials of degree at most k minus 1, something like that. Yes. But in particular, Gaussians are the extremizers. So from this, I only need a very silly observation that this is an equality for the Gaussian function, for the standard Gaussian function with this ugly constant. And I also need the philosophy behind the estimate that it's probably best to plug in to my inequality something that looks like a Gaussian. Something that comes as close to the Gaussian as possible under the constraint that it lives on this discrete interval, right? And the best I can do, of course, is try to imitate it that way. I'm plugging in some like Gaussian restricted to this. Like this, of course, it's centered at the center of this interval, somewhere at the midpoint. That's the best you can do, right? And you plug it into this inequality with some sharp exponent p sub k n that you don't know. It's related to those t sub k n by the previous proposition. And now you compute. Now actually you realize that in the limit, when n goes to infinity, those quantities converge to this thing, where this is just a truncated standard Gaussian, and these quantities converge to this thing, even though it's conceptually easier to prove that the upper limit is less than or equal to that. This is enough, right? But morally, probably it also converges to that. It's just awkward because I have a difference, and yeah, somehow it's easier just to prove that the upper limit is at most that. But surely in the end, you know that actually this converges to the same thing. And then take logarithms and subtract, and you realize that the lower limit is at least that much. Now take the limit m goes to infinity to have not the truncated but the true Gaussian, and you get this ugly constant, and this is what you have in the lower bound. This is how you get the lower bound. This is what you guess to be the best you could do, but you don't know it. You don't know it, and even for the additive energy, it's open. In his paper, Shao has some philosophy why it probably should be the precise asymptotics, but it's tricky. What about the upper bound? The upper bound is something that we're not going to talk much about because Shao proves the upper bound precisely by applying his sharpened Hausdorff-Young. That's it, right? And we cannot do anything better. All we could do is to show that actually these t's grow at most by 1 by increasing this degree k, which is a consequence of this recursive definition of the Gowers norms. So pretty much apply the induction hypothesis to this function, simplify and realize that the inequality holds with this exponent, so this is the minimal one, so that's why I have the inequality. So it's a legitimate question why we're not getting anything better and why we're not tracking down dependence in K. That's actually a very good point, because Shaw's inequality is just one Hausdorff-Young, or equivalently just one sharp Young's convolution equality. Here we're applying it in each step, but we're applying the usual one, the non-sharpened one. Because if we apply the sharpened one, I'm not 100% sure that we are able to get anything. Because, you know, these improvements can get smaller as K increases, because the points somehow approach to the boundary of the region where you don't have an improvement. So I'm not 100% sure, but it might easily be that we're just summing a series of constants, which is just another constant. And then since this constant was just arbitrary, I just cannot really guarantee anything about the growth. But in any case, I don't think we can anyhow match the lower bound, which grows roughly like K log K. This seems to be out of reach anyway. So maybe we didn't try hard enough, but I don't see how imitating what Shao did can anyhow improve this constant. So the best we could do is just apply his estimate as a black box and got this, which is kind of good enough on a larger scale, but not very precise. Finally, the last part is the asymptotics in K, right? So now fixing the cube and letting this number K go to infinity. So at least for large K's, you know what the exponent roughly is. Right? It goes roughly like a log K, but you even know the constants and everything. Here's how the entropy comes into play. Let's recall that the Shannon entropy in the binary convention of a random variable with this distribution supported on the integers is this quantity, a negative sum, the probabilities times the log of the probability, right? This is what's the definition. I'm measuring in bits, not in nets. So, and we also denoted that H sub n, that was the entropy of the standard, of the symmetric binomial distribution. Okay, so what do we do for the lower bound? For the lower bound, we try again to do the same thing, somehow plug in something that we expect to be an extremizer, which is something that imitates Gaussians. But if you're fixing the cube, you have a canonical choice. You have a binomial distribution is the best that you can do, like on a fixed cube. Now the interval is fixed, so why not plug in that? Before, just realize that only certain terms matter. All others are somehow smaller order. So in this inequality, which is just the 1D inequality that you're testing, right? This is just the 1D inequality, the optimization problem that I mentioned. I disregard all terms, but those that are of the following forms. You see, this number A is from 0 to n minus 1. It's arbitrary. And precisely A of these numbers, H, are actually equal to -1. So you never go below 0. Precisely n minus 1 minus A are equal to 1. So you never go above n minus 1. These numbers always stay in the range. So in the support of F. Right? And all other H's, because you have many, if K is very large, all others are equal to 0. Right? So what you get by considering these terms, this is how many terms you have, because of K H's you needed to pick n minus 1s that are non-zero, and you had to distribute the signs in that many ways. And all those terms led to the same quantities, right? So you see, this is actually somehow binomially distributed, right? I mean, over all possibilities. So the exponents actually look like that. Okay, on the right-hand side you still have the same thing. So now plug in this function. So here you see the binomial distribution raised to a proper power so that this cancels. So that on the right-hand side you get 1. On the left-hand side you get what you get, right? Some ugly thing. But then you take logarithms, and you realize that the entropy of the binomial distribution appears naturally, times t, so kn. And this is just roughly log k times times n minus 1 plus something small. Take this to the right-hand side, and you get the lower bound. It's nothing crazy. It's actually very, very simple. What do you do for the upper bound? For the upper bound, you actually have to prove an inequality, right? You have to prove an equality with a given exponent, but for all functions f. That's the harder part. And that's the last part, of course. You have to prove something that looks like this, where I intentionally grouped the terms. How did I group the terms? I grouped the terms by what is actually important. This regarding those h's that are 0. So those h's that are 0 are only going to contribute to the coefficient here, right? So if L of those h's are non-zero, I group the terms according to what they are, right? And all other h's are 0, and I just need to choose L non-zero h's out of k h's in total, so that all other h's only contribute here to the coefficient and to the exponent, right? Because you're going to see the same numbers multiplied many times, because if some h's are 0, you don't really see them in the sum that you had before. Only those h's that are non-zero are now remaining in this argument. So this is actually the same inequality, just with terms grouped. So these are the types of the terms according to which h's are non-zero. These are the simplest terms. They are not very interesting. If no h's are non-zero, you have just a single point, right? That repeats to the k times, and that's it. So we have to prove this. And you also substitute to make it look a bit more simpler. So to prove this inequality for functions, taking only n values in total, and we can also impose this constraint that the sum of these values is 1 by homogeneity to actually prove that something is only less than or equal to 1. And what do we need to prove? We prove it for t, which is that much, for any previously given delta. So if I want to prove that the minimum over all t's is just this much, it's sufficient to give yourself a room, take an arbitrary delta greater than 0, and prove that inequality is satisfied with this t, and then in the infimum, in the limit, of course, you get that the smallest t is that much, but I need to prove that this holds for all sufficiently large k, depending on delta and depending on n. That is allowed, right? So that's all you need to do. So how do you do it? Just when you started grouping the terms, except for these terms that I said that are trivial, they still need to be handled by splitting into cases when they are dominant and when they're not, but they're not very interesting, so I'm not going to discuss them. I'm going to discuss all other terms that are more interesting, and these are of the following form, as we saw in the inequality, right? This is what appeared, and those exponents were actually just the distribution on this set of this random variable. So instead of epsilons, I'm writing x's, right, which are just independent symmetric Bernoulli trials, right? So what you actually see, actually this is the distribution of this random sum. So how do you bound these terms? Very simply by arithmetic geometric mean, just with weights. Start with this. You know that this was our constraint enabled by homogeneity. The sum of g's is written this way. Now you apply the weighted arithmetic geometric mean to write it this way, and then just simplify, and you realize, oh, I can actually bound this product by the denominator and raise it to t and multiply with the binomial, and you immediately get that this inequality, and when you multiply, you get that each term is bounded precisely by k chose L due to the negative entropy that you had to multiply with t, okay? For each of those terms. Where I only consider terms that have precisely L non-zero h's here, right? Okay, now I remember what t was. I didn't choose it arbitrarily, of course, we chose it carefully, plug it in, and simplify. So first, you might expect, well, I'm going to go back, right? You might expect that the most important term is the same one as before, when precisely n minus 1 h's are non-zero. Because then this binomial coefficient is the polynomial of the largest degree, of the degree n minus 1. It's not that trivial because you also have dependence on L here, right? So you're not really sure. This will be the case, but it's not immediate. So when you plug things inside, you realize, okay, for this main term it's okay. This all simplifies to some number times this. I chose it very carefully to have something smaller than 1, and also the correct number of times that this term will appear in the estimate. But the rest, all other terms should be of smaller order. How do I know that? Because when I see what is the degree of k here, it's L, right? And when I plug in what t was, blah, 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 well, of course, it involved all those numbers, but when you simplify, it turns out that the exponent is L minus n minus 1 times this entropy divided by the entropy of the binomial for all h is strictly smaller than n minus 1. Oh, so you would like this exponent to be negative in order for this to go to 0, right? Okay? So the strategy is now to sum over all terms. So as I said, those terms with n minus 1 or 0 h's, they all contribute with something strictly smaller than 1. I left myself a little bit of room for the error, for large k. All other terms will go to 0 in k if I know that the exponent I told you about is negative, which is equivalent to this inequality. And that's a quite tricky inequality for entropies that you couldn't immediately prove, right? I mean, it looks very, very simple, but you have to verify it over all possibilities of h's, over all non-zero vectors h, right? And there is, there is infinitely many possibilities. Luckily, also for a fixed n, there is only finitely many possibilities because you know that you only need to consider distributions that are supported in an interval of length n. So more or less finitely many cases, but there are still quite a few cases. All we could do using a computer was up to 12, or n was like less than 12. But we could do it, okay? So what is left, just to prove, and then I'll be done, is just to prove this inequality for entropies, right? For any n at least 2, any L less than n, for any non-zero vectors, you want to prove this inequality, and you also want to prove that equality is attained only when here you see the symmetric binomial distribution. And precisely this one, right? With precisely n minus 1 trials. Okay? And one can do it, and I just prepared like a beautifully ugly proof, which actually shows it first for n is greater than 100, just by using several estimates for entropies and asymptotics like this one, even though this is still needed. And then you have to reach to 100, so you can only run a computer up to 12 or so you have to combine the two things. It was super ugly and super exciting, but we did it. And I left something for you as an open problem, but it was solved a few days ago by another great student in Zagreb, actually, who yesterday sent me the proof, and it's beautiful, flawless, and I had to include him as an author, of course, because now pretty much no computer-assisted verification is needed, even though something slightly ugly is. So what is the strategy? The strategy is actually to first optimize for a fixed number of terms, right? For a fixed number of terms L, you wonder when this is minimal. You expect this to be minimal also in the same case when you have the binomial distribution. Okay, so these numbers decrease as the number of terms increases. So which is seen, okay, this is still not entirely nice. You need some very precise bounds for the entropies of the binomial distributions. But these can be found in the literature. You can find many terms. It's not enough to have asymptotics. Right? You just want precise bounds to be 100% sure that this actually holds. But after this, everything is just reduced to just minimizing the entropy for the fixed number of terms. So if you fix a number n, and you have n non-zero numbers, it turns out the entropy of this sum, of Bernoulli trials multiplied by those h's, is minimized precisely for the symmetric binomial distribution. Or in other words, when all those h's are the same in the absolute value. And this is what I couldn't prove, and I said I just prepared this as a nice problem that maybe we can talk about, but actually it turns out to have somehow shamefully simple proof, a very elegant one. So here is the proof. Actually, you can consider the probability mass functions of this random sum that you have, quite the arbitrary one, and of the binomial distribution that you suspect is minimizing the whole thing. And consider their decreasing rearrangements, right? I denote them this way. First, you apply Karamata's inequality to this strictly concave function, which defines the entropy. So Karamata's inequality says that sums of convex or concave, whatever, let's say, convex functions were applied to elements of certain vectors are greater than the same for the other vector if the first vector majorizes the second one. And the majorization is what you would expect. The largest component here is larger than the largest here. The sum of the first two largest here is larger than the sum of the first largest here, and 3, and so on, all the way to the end. Okay, so it's actually enough to see that the binomial distribution, when sorted in descending order, majorizes a distribution of any form of this form. Always, inequalities attained only when they're the same. But this is a combinatorial problem, actually. So by switching from probabilities to enumeration, you just multiply by 2 to the m, right? Just enumerate and realize that for a fixed z, because this is what a probability mass function does. It detects the probability that the random sum is precisely z. This, when you consider all sets leading to z, so instead of 0 and 1 coefficients, I can consider subsets of 1 to the m. So the collection of all such sets for a fixed z is an anti-chain. Right, because, I mean, of course, one cannot be contained in the either, because then you have a subsum also equaling z. There is a slight also thing that I realized that I need to put here. You can usually reduce to cases h is positive. It's just by symmetry in the problem. You can always reduce the case when h's are positive. This only shuffles the sum, but the distribution remains the same. So if those h's are positive, then of course you're adding more terms, you're getting a larger quantity. Both cannot be z. So actually this is an anti-chain. And now there is something called Sperner's theorem, which tells you what is the size of the largest anti-chain. But there is a generalization. Even the old Erdős generalization tells you what is the maximal size of the union of n disjoint anti-chains. And it is again what you would expect. It is precisely the sum of the n largest binomial coefficients, or the form m choose something. And this is precisely what you get for the binomial distribution, divided by 2 to the m. And you're done. Yes. And that's it. That's the whole proof. It's actually very, very simple. Sorry for going slightly over time. Thank you.